Hello everyone, this is Shuaishuai. Today I'm going to talk about extrinsic polarons, engineering coexistence between free and trapped carriers. A polaron is a quasi-particle used to understand interactions between electrons and atoms in a solid. We all know that electrons move freely in metals. However, in some ionic or highly polar materials, electron can be trapped and it will push its surrounding atoms away from their equilibrium position. We call this trapped electron or hole together with the surrounding lattice distortion a polaron. Polarons move slower than free electrons because it has to drag all the lattice distortions with it when it moves through this solid, so electron or hole mobility can be greatly decreased by the formation of polarons. Many energy materials suffered from polaron formation, so we would like to further understand the mechanisms of polaron formation in order to help improve the performance of many energy devices, and that's the motivation of our research. Let's first look at some examples of intrinsic polarons. Intrinsic polarons is self-trapped, that is to say they can form imperfect materials. One example is that we previously find electron polaron forms easily in a bunch of peroxides such as lithium peroxide, sodium peroxide, etc. Another example is that many transition metal oxides such as titanium dioxide, hematite are prototypical materials to form polarons. In these perfect intrinsic materials, there are two states. One is a delocalized state and the other is a polaron state. And there is usually no barrier or a very small barrier separating these two states. From the electronic band structure point of view, it can be viewed as a conduction band minimum is already composed of the orbitals the electron will be localized on in the end. Once there is an excess electron, the state lowers directly from the CBM. So there is only a negligible barrier separating the two states. Next, let's take a look of extrinsic polarons. Instead of forming imperfect materials, extrinsic polarons bind with some defects. For example, point defects on the titanium surface may lead to polaron formation directly near these defects. Our previous work on sodium chloride F+ center, a localized charge on the chloride vacancy in sodium chloride, is also one kind of extrinsic polarons. Here is another example of tin-doped hematite. We can clearly see that a polaron forms nearby the defect site. In these cases, we usually see a spontaneous polaron formation. There is no barriers at all, since the lowest unoccupied state is already within the bandgap prior to electron insertion. The excess electron undergoes a barrierless relaxation from a gap state to a more deeply trapped polaron state. So in these cases, only localized state exists. In the examples above, there is either only localized state or a tiny barrier separating the two states. However, in some applications, such as resistive switching or memoristor devices, we would like to have the coexistence of delocalized and localized state. So in this work, we would like to answer how to achieve the coexistence of delocalized and localized state via extrinsic polarons. Now let's look at our design ideas. We want to have both delocalized states and localized state. The delocalized state here refers to free electrons in the conduction band, such as the CBM of tin oxide and gallium oxide. And localized state usually shown in transition metal oxide, where the metal cations have unfilled d orbitals. How can we combine the two to create coexisting localized and delocalized state? The special thing in our work is usually people dope to get more free carriers, but here we dope a localized component. We use materials have S-like orbitals as host materials to provide the dispersive CBM and the transition metal cations as a dopant to introduce the localized state. And we use electronegativity as a guidance to place the dopant level above the CBM. And based on the design ideas, we find the one material system, titanium doped tin oxide, that suits all those criteria. Then we calculate its p-dose of this material. We can see that dopant is indeed above the CBM. And once the extra electron is added to the system, at the delocalized configuration, the extra electron is at the conduction band minimum, and the dopant level is above the CBM, and the extra electron is shared among all the orbitals of tin oxide, while at localized configuration, the dopant level is lowered down below the CBM, and the extra electron is localized on the single titanium dopant. And this is exactly the coexistence domain that we want to achieve. Next, we do a linear interpolation between delocalized state and localized state. The localized state is initially less stable than the delocalized state. Moreover, there is a maximum separating the two local minima. Now that we have obtained the material system with coexisting states, can we further tune the transition properties such as the barrier height and the relative stability between the two states? Next, we will investigate the transition process on the various strain and doping concentrations. For example, on the various strain, we alter the delocalized state being more stable to localized states being more stable, and we change the activation barrier from 0.6 electron volts to almost 0 electron volts. We can understand this by separating the total energy into two parts, lattice strain penalty and electronic relaxation. The lattice energy are about the same on the different strain, but for the electronic relaxation part, they have apparent differences. We can see that with larger compression, it has less delay of electronic relaxation. The energy level lowers down much more quickly so that there leads to small barrier on the compression strain. We can achieve more insight from the project densive states. We can see with the increase of the compression strain, the gap between the grain defect and the conduction band minimum decreases. The smaller gap between defects A and CBM lead to smaller barrier between the delocalized and localized states. In addition to strain, we can also vary the doping and alloying concentration. Here are the crystal configuration and the band structure as we increase the titanium concentration. The green dots are the titanium atom and the blue dots are tin atom. With increase of titanium atom, we can see how the effective band structure changes, and the green titanium contribution moves down and dominates the CBM step by step. From the p-dose plot, we can see the same thing. The green titanium band increases and the gap between the dopant and CBM decreases. If we plot energy curve between the delocalized and localized states at various doping concentration, we can see the formation barrier decrease from about 0.6 electron volts to almost 0 electron volts, and the formation energy also varies as doping concentration changes. In the end, we find two parameters that play dominant roles in engineering the barrier height. We then apply a phenomenological type binding model to further investigating the mechanism of such engineering by tuning two parameters. Let's take a closer look of the two parameters. Delta A is just the gap between the dopant level and the CBM. We can change the lattice dependent potential of epsilon BB in the type binding model to change delta A and the gap between the dopant level and the CBM. So by varying delta A, we change the barrier height. In this case, it's more like string engineering. WD is the bandwidth of the dopant elements. We can change the hopping term VBB in the type binding model to change the bandwidth WD. So by varying WD, we can also change the barrier height. This case is more like tuning by alloying. We notice that the formation energy changes less linearly. It decreases and then increases. Because changing WD will also change delta A, so there are competing factors for the relative stability of the delocalized state. So by using the type binding model, we more clearly show the mechanisms of such engineering. By change delta A or WD, we can tune the barrier height and the relative stability of this carrier localization transition, and this also connects with the ab initio results of string tuning and alloying. Let me use this diagram to sum up today's presentation. We classify different types of electron polaron formation based on their initial and final states relative to CBM. And what we typically say is there is either no delocalized states near defect or negligible barrier separating delocalized and localized states. In this work, we place a localized orbital above the CBM and achieve the full coverage of Polaron formation. We arrive at a regime where delocalized and localized states can coexist, and there is a finite barrier separating the two states, which can further be tuned by straying or alloying. This tuning mechanism is revealed through epi-initial capitalizations and phenomenological type binding model. We hope this can provide another parameter for engineering device properties in the future. Last but not least, I would like to sincerely thank my supervisor, my group members, and I would like to acknowledge all the funding agencies. Thank you very much for your attention.